Wireless sensors can monitor how temperature, humidity, or other environmental conditions vary across large swaths of land, such as farms or forests. These tools could provide unique insights for a variety of applications, including digital agriculture and monitoring climate change. One problem, however, is that it is currently time-consuming and expensive to physically place hundreds of sensors across a large area. Inspired by how dandelions use the wind to distribute their seeds, a University of Washington team has developed a tiny sensor-carrying device that can be blown by the wind as it tumbles towards the ground. This system is about 30 times as heavy as a 1 milligram dandelion seed, but can still travel up to 100 meters in a moderate breeze, about the length of a football field, from where it was released by a drone. Once on the ground, the device, which can hold at least 4 sensors, uses solar panels to power its onboard electronics and can share sensor data up to 60 meters away. Senior author 𝙪𝙗𝙨𝙧𝙩 says, "We show that you can use off-the-shelf components to create tiny things. Our prototype suggests that you could use a drone to release thousands of these devices in a single drop. They'll all be carried by the wind, a little differently, and basically you can create a 1000 device network with this one drop." This is amazing and transformational for the field of deploying sensors, because right now it could take months to manually deploy this many sensors. Because the devices have electronics on board, it's challenging to make the whole system as light as an actual dandelion seed. The first step was to develop a shape that would allow the system to take its time falling to the ground so that it could be tossed around by a breeze. The researchers tested 75 designs to determine what would lead to the smallest terminal velocity or the maximum speed a device would have as it fell through the air. Lead author 𝙪𝙗𝙗 says, "The way dandelion seed structures work is that they have a central point and these little bristles sticking out to slow down their fall. We took a 2D projection of that to create the base design for our structures. As we added weight, our bristles started to bend inwards. We added a ring structure to make it more stiff and take up more area to help slow it down. To keep things light, the team used solar panels instead of a heavy battery to power the electronics. The devices landed with the solar panels facing upright 95% of the time. Their shape and structure allow them to flip over and fall in a consistently upright orientation, similar to a dandelion seed. Without a battery, however, the system can't store a charge, which means that after the sun goes down, the sensors stop working, and then when the sun comes up the next morning, the system needs a bit of energy to get started. The challenge is that most chips will draw slightly more power for a short time when you first turn them on," 𝙪𝙗𝙗 said. "They'll check to make sure everything is working properly before they start executing the code that you wrote. This happens when you turn on your phone or laptop too, but of course they have a battery." The team designed the electronics to include a capacitor, a device that can store some charge overnight. Then we've got this little circuit that will measure how much energy we've stored up, and once the sun is up and there is more energy coming in, it will trigger the rest of the system to turn on because it senses that it's above some threshold, he added. These devices use backscatter, a method that involves sending information by reflecting transmitted signals to wirelessly send sensor data back to the researchers. Devices carrying sensors measuring temperature, humidity, pressure and light sent data until sunset when they turned off. Data collection resumed when the devices turned themselves back on the next morning. To measure how far the devices would travel in the wind, the researchers dropped them from different heights, either by hand or by drone on campus. One trick to spread out the devices from a single drop point, the researchers said, is to vary their shape slightly, so they are carried by the breeze differently. This is mimicking biology, where variation is actually a feature rather than a bug, said co-author Daniel. Plants can't guarantee that where they grew up this year is going to be good next year, so they have some seeds that can travel farther away to hedge their bets. Another benefit of the battery-free system is that there is nothing on this device that will run out of juice. The device will keep going until it physically breaks down. One drawback to this is that electronics will be scattered across the ecosystem of interest. The researchers are studying how to make these systems more biodegradable. This is just the first step, which is why it's so exciting, 𝙨𝙪𝙥𝙗𝙧 said. There are so many other directions we can take now, such as developing larger scale deployments, creating devices that can change shape as they fall, or even adding some more mobility that devices can move around once they are on the ground to get closer to an area we're curious about. Meanwhile, with carbon dioxide emissions reaching approximately 40 billion tons from both fossil fuel and land use, it has become a major challenge for the world to either decrease or recycle it. Previously, we presented the stories of researchers from the University of Delaware who created a battery to recycle carbon dioxide, and the Hokkaido University who developed a way to recycle carbon dioxide into useful drug development molecules. Now, engineers at the University of Cincinnati have developed a promising electrochemical system to convert emissions from chemical and power plants into useful products while addressing climate change. These engineers, led by Assistant Professor Wu, used a two-step cascade reaction to convert carbon dioxide to carbon monoxide and then into ethylene, a chemical used in everything from food packaging to tires. Zhang, one of the study's lead authors, led a similar study last year that examined ways to convert carbon dioxide into methane that could be used as rocket fuel for Martian exploration. The significance of two-stage conversion is that we can increase the ethylene selectivity and productivity at the same time with low-cost strategy, Zhang said. This process can be applied to various reactions because the electrode structure is general and simple. Selectivity means isolating the desired compounds. Productivity is the amount of ethylene the reactor can produce. We're selectively reducing carbon emissions into something considered valuable because of its many downstream applications, Zhang said. Applications include a variety of industries from steel and cement plants to the oil and gas industry, he added. In the future, we can use this technique to reduce carbon emissions and make a profit from it. So reducing carbon emissions will not be a costly process anymore, he said. Ethylene has been called the world's most important chemical. It's used in a range of plastics from water bottles to PVC pipes, textiles and rubber found in tires and insulation. Wu said the chemical they produce is known as green ethylene because it is created from renewable sources. Ideally, we can remove greenhouse gas from the environment while simultaneously making fuels and chemicals, Wu said. Power plants and ethylene plants emit a lot of carbon dioxide. Our goal is to capture the carbon dioxide and convert it to ethylene using electrochemical conversion. So far, the process requires more energy than it produces in ethylene. By using tandem electrodes, UC engineers were able to boost productivity and selectivity, both of which are key indicators toward making the process commercially attractive to the industry. Wu said there are huge environmental advantages to containing and converting greenhouse gases. It's being pushed by the government. In the future, we'll need sustainable development, so we'll need to convert carbon dioxide, he added. Wu further stated copper isn't necessarily the best catalyst for this reaction, so industry experts have likely alternatives that could boost productivity and efficiency even more. Our system is very general, but you can use preferred catalysts. But even with commercial copper, we were able to more than double the performance. With an even better catalyst, we could solve the economic issue. Zhang said the system will take some time to become economical, but already they have made tremendous strides. The technology has improved a lot in 10 years, so in the next 10 years I'm optimistic we'll see similar advances. This is a game changer, Zhang said. Speaking of cleaning the environment, microbiologists from Radboud University have demonstrated that it is possible to make a methane-consuming bacteria generate power in the lab. The bacteria Candidatus methanopteridans use methane to grow and naturally occur in fresh water, such as ditches and lakes. In the Netherlands, the bacteria mostly thrive in locations where the surface and groundwater are contaminated with nitrogen, as they require nitrate to break down methane. The researchers initially wanted to know more about the conversion processes occurring in the microorganism. In addition, they were also curious whether it would be possible to use it to generate power. This could be very useful for the energy sector, says author Welt. In the current biogas installations, methane is produced by microorganisms and subsequently burnt, which drives a turbine, thus generating power. Less than half of the biogas is converted into power, and this is the maximum achievable capacity. We want to evaluate whether we can do better using microorganisms. Fellow microbiologists from Nijmegen have previously shown that it is possible to generate power using Anamox bacteria that use ammonium during the process instead of methane. The process in these bacteria is basically the same, says microbiologist Oboter. We create a kind of battery with two terminals, where one of these is a biological terminal and the other one is a chemical terminal. We grow the bacteria on one of the electrodes, to which the bacteria donate electrons resulting from the conversion of methane. Through this approach, the researchers managed to convert 31% of methane into electricity, but they aim at higher efficiencies. We will continue focusing on improving the system, Welt says. With so many researchers developing incredible methods to tackle the environmental problem, it seems we are heading in a very bright direction, and sustainability is not just a theory anymore. What are your thoughts on this and these amazing discoveries? Do let us know in the comments.